Hello everyone. In this lecture, we want to talk about higher order derivatives. Okay, this is the first time we talk about it. Imagine we have a quartic function here. It's a polynomial function, and it's needless to say that the derivative of the function, which is shown with the prime notation f prime of x or y prime, is equal to 4x cubed minus 3x squared plus 4x plus 6, obviously. Okay, this is the derivative of the function. We call it first derivative. Now, imagine that the first derivative itself is a cubic function, is it not? So if it is, then we are trying to find the derivative of the derivative. We call this second derivative of the function. So the notation we use is y double prime, okay? And that is the derivative of the derivative. So here we get 12x squared minus 6x plus 4. And as you see, the second derivative is becoming quadratic. So originally we had a quartic function whose derivative was a cubic, and now the second derivative is becoming quadratic, obviously. And you can show this with the notation of f double prime of x as well. The third derivative would be y triple prime or f triple prime of x, and that will be 24x minus 6. But then the thing is that we cannot add these primes, okay? Because imagine if you want to take the derivative function like 20 times, you can't put like 20 primes right there. So that's why mathematicians had to come up with some sort of notation. And that notation is the following. They put like a 4 at the top. 4 meaning like the fourth derivative. But the thing is that when they put the 4, people said, okay, so how would you distinguish between y raised to the exponent of 4 and the fourth derivative of the function y? How would you distinguish? So it was a valid point. Therefore, mathematicians said we are going to put these inside brackets. Okay, so when you see that the exponent has brackets around it, it doesn't mean exponent. It means the fourth derivative of the function. And furthermore, they said it is better to use the Roman numerals actually. So they're using Roman numerals inside the brackets so that it's like crystal clear that they're talking about the fourth derivative of a function and not an exponent of 4, clearly. So here we go f open brackets, Roman numerals 4, close brackets, of x equals, and that's the fourth derivative of the function. In this case, it's going to be 24. The fifth derivative would be y, and then I use Roman numerals here. And of course, it would be 0. And I can write f and then brackets, Roman numerals 5 of x. And from that step on, I would say if I put like the sixth derivative or the second derivative of the function using Roman numerals and brackets, all of those up to the nth derivative of the function would be 0 from this step on, because we ended up with 0 after 1, 2, 3, 4, 5 steps, right? Okay, so one thing we noticed is that the fifth derivative of a fourth degree polynomial function was 0. So we conclude that if you have an nth degree polynomial function, n plus first derivative would be 0, basically, right? So this is a conclusion we came up with. We can say for a polynomial of degree n, okay, the n plus first derivative is always 0. That's the conclusion we come up with, and it makes sense because when you take the first derivative of a quartic function, you end up with a cubic polynomial. When you take the derivative of the cubic, you get quadratic. Quadratic becomes linear. Linear becomes constant, and derivative of a constant is 0. So 1, 2, 3, 4. The fourth derivative was a constant, okay? So that means that the fifth derivative must be 0. So, and this was a fourth degree polynomial function. So generally speaking, for a polynomial of degree n, the n plus first derivative is always 0, obviously, okay? Take, for example, quadratic function, x squared. So if it's like x squared to the degree is 2, that means that the third derivative is 0. And you know that the first derivative is 2x, the second derivative will be 2, and the third derivative is derivative of 2, which is 0. There you go. You see, it works for every polynomial, actually. Other notations that we are using, I wanted to mention. One is the famous Leibniz notation, so dy over dx. But for the second derivative, we say d2y over dx squared. That's the notation. d3y over dx cubed, d4y dx to the 4. And for the nth derivative, we say dny over dx to the n. That's the Leibniz notation for the higher order derivatives. And you can, of course, write other ways. For example, you can say d2 over dx squared of f of x, for example. Or like d3 dx cubed, meaning the third derivative with respect to x of f of x, for example. Or you can say d4 dx4 of f of x. These are like other notations. There's another notation, d of y with respect to x, capital D operator, they call it in the old textbooks. So this would look like d2y sub x, d3y sub x, or d4y sub x. Or you can say dn of y with respect to x, which means the nth derivative of y with respect to x. That's another notation. So the most popular notations are prime notation and Leibniz notation, which you have to know it in and out. It says another question here. It says, given f of x equals the rational function here, it says find f double prime of x. Okay, so they're looking for the second derivative. So we're going to find the first derivative, f prime of x. U prime b is going to be x minus 1 minus derivative of bottom, which is 1 times top, over the bottom squared. If I simplify, I get negative 1 over x minus 1 all squared. So this is the first derivative. I applied quotient rule to find the answer. Now, I can rewrite this as negative 1 times x minus 1 raised to the exponent of negative 2, mind you. And in order to find the second derivative, I'm going to apply chain rule combined with power rule. So I'm going to say this negative sign remains unchanged. I have u to the exponent of n, whose derivative is n times, that is negative 2 times, u prime, which is going to be 1, derivative of the inside, and then times u to the exponent of n minus 1. So x minus 1 to the exponent of minus 2 minus 1, which is negative 3. Now, simplifying this is going to give me 2 over x minus 1 cubed. So this is the final answer the question was looking for. It asked us to find the second derivative of that function, and that is the second derivative. The first derivative was negative 1 over x minus 1 squared. That was the first derivative, and this is the second derivative. Now, you can continue to find the third derivative or the fourth derivative, well, depending on whatever the question is asking. Given the function y equals 3 over 2x plus 3 over x minus 4x squared, it says show that this expression is true. Now, in this expression, we see y triple prime, we see y double prime, or y prime. So I think the best thing to do is to find these higher order derivatives before anything else. So I'm going to differentiate. I'm going to say y prime is going to be 3 over 2 minus 3 over x squared. That's the derivative of 3 over x, and then minus 8x. And then the second derivative would be the derivative of negative 3 over x squared. If you rewrite this as, let's say, negative 3x to the exponent of negative 2, if you think of it like that, then what is the derivative of this? It's going to be 6 times x to the exponent of negative 3, basically. And the derivative of that would be negative 8. And the third derivative would be negative 3 times 6, negative 18x to the negative 4, and that is 8. So these are the higher order derivatives, and I didn't explain how you find them because I believe you know the basic differentiation rules. Otherwise, you wouldn't be watching this lecture. And now we just have to do the substitution to see if we can prove left side equals right side or not. So we start with the left side, which is x cubed times y triple prime plus x squared y double prime minus 2x times y prime plus 2y, and negative 18x to the negative 4 plus x squared times 6x to the negative 3 minus 8, and then minus 2x times y prime, which was that expression, 3 over 2 minus, we need more room, so I'm gonna, unlike what I don't like to write in the second line, but what can I do? So negative 2x times y prime, which was there, 3 over 2, we're gonna copy, and then plus 2y, twice y would be 3x plus 6 over x minus 8x squared. Okay, so let's do the math here. We have negative 18x cubed over x to the 4. If I multiply, I get plus 6 over x minus 8x squared. 2 and 2 cancel out each other, minus 3x plus 6 over x, actually. X and x squared, they cancel out each other. And then negative times negative is positive 16x squared plus 3x plus 6 over x minus 8x squared. Okay, so this one becomes negative 18 over x if I reduce. 6 over x, 6 over x, 6 over x, that's going to be 3 times 6 over x, which is 18 over x. Negative 8x squared, negative 8, that would be negative 16x squared. With that positive 16x squared, they cancel out each other. Negative 3x plus 3x cancel out each other, so that will be 0. And these two also be 0. Therefore, we see that left side equals right side. You just have to be patient and one by one, do the substitutions and do the expandings and simplifying, with perseverance. And then finally, you will see that the answer is 0. And the statement you were supposed to prove, you can, of course, prove it. Okay, so this lecture was about higher order derivatives. We learned about notation. We learned about what is higher order derivatives. Later, we will learn about their applications. We did one question here. We found the second derivative of a rational function. And we also did another exercise just as an example. So keep practicing, and thank you for your attention.